for 50 years, 50, huh? And yeah, that's right, I'm old. And it's been really nice for me to have such good colleagues that I have there. But I'm pretty simple in what I do usually. Well, almost always, I guess. So recent advances in evaluating the linear and nonlinear dynamic properties of rock subjected to earthquake shaking. I had to say the earthquake shaking because that's where we are here, but no, we're really looking at rock. And the thing, if you go out in the field like I do so often, and we might be making seismic measurements with various pieces of equipment, and the drillers are out there, and then you see what they do with the rock samples that come out of the ground, and they take them to the trailer, and that maybe at 105 degrees, because it might not be air conditioned. It's amazing how most people think rock can't be hurt. Wrong. If you handle it incorrectly, you're going to get numbers back from the laboratory, if that's where you're sending it, that may not be very good. And by the way, water content can affect rock quite a bit. I'll try to remember to get into that a little bit, but we'll see where we go. Oops, is that what I aim at, or is this what I aim at? Or have I turned things off? Uh-oh.
Yes.
No, not the pointer. I want to advance my slides. Yep.
No, going down.
Going down?
Yes.
You're right. Thank you. Okay, so I like torsional resonant columns, just for the record, if you don't know. And that's what this is. And I will show you, oh, dang it, I'm going to have to get some things out from down there in a minute. But I'll show you what we have been doing now with rock, and gives us a better idea, in fact, of how good it is, how much it might change, and so forth. Okay, and this is a combined resonant column and torsional shear device. Yep. Oh, now I have that. Okay, torsional shear device, and what you see, this is the top view of it, and it's got, 4 arms. Each magnet in coils will push or pull, and they're all in sequence. If you want to do slow cycling, you use this proximeters right here, so it measures the gap between that one in the target and this one in the target, both, so that you cancel out any minor bending, because it really won't bend very much. And in resonant column, here's this is crazy, isn't it? I don't aim at that. Okay, there's the accelerometer that we use to do resonant testing. So we can make damping measurements at high frequency, or and stiffness measurements, or we can do so that the proximeters would give you a hysteresis loop, okay, when you're cycling. You're back here to help me? That's okay. Any help would be helpful.
Pointer.
Okay, that one. I like it. Better than that arrow. Okay, but now I can draw my hysteresis loop a little bit better. And your resonance would be, you're looking at a resonant peak and so forth. Okay, here's a specimen down here. It may look a little goofy here, but that's because we got the 4 arms and you only see one of the arms. There's the proximeter, there's the accelerometer, and of course, for rock, you don't really need height change measurements because it's not changing, but for soil, you need the height change measurements as well. Okay, and that's what we're going to be looking at. Whoops. That's what we're going to be looking at. And so here's a rock specimen. When rock specimens come into us, they might be in longer pieces, and we will take and cut them to a reasonable size, to a length, and then we may do something a little bit more, and I forgot to bring it up here. Don't worry, this is going to be a surprise to you. And I had this specially made for this talk. This is the only way I'm going to talk for 30 minutes. I don't have much to say, so I got to stall. No, I'm teasing. Okay. So the rock specimens you're going to see. Now, do you think I'd pass a rock specimen around? No way. There's an aluminum specimen the same size. Okay, thank you.
I can take it for you.
You need to. Okay, thank you very much. This is really hectic, isn't it, that I've made it. But in this talk, all the specimens is there. You're turning that off for me, thank you. So that's the size of the rock specimen we'd have. Now, we have to send it, we have a lab in Houston, Texas, where we send them, and they do NQA1 work, Nuclear Quality Assurance Level 1. All of this has been done in that, because it's been at other sites where we have to have that calibrate before, calibrate after you've been to the site, and so forth. But this would come out of about that diameter rock specimen. And when it came into the lab, we would test it in a free mode. And that is, we can measure shear modulus and material damping and shear. We can measure Young's modulus, material damping and Young's modulus. And we can measure constrained modulus. Now, on that rock specimen, we tap in the middle and send a very high frequency wave, means a very short wavelength, down from one end to the other of that sample. So we will do that when we send the big piece down to the lab to carve it. And when we get it back, we'll do it again with this one. Now, there's some other that we can't do it with. I won't show you data on this now, but that's the smallest rock specimen we can test in this piece of equipment. And that's what we're doing now, hollow rock specimens. When you're resonating them, you get such an accurate measurement, it's beautiful. But I wanted to show you those specimens, but not the real ones, because they cost a lot more than these once you take them down to the lab. Okay, so here we are. We're looking at testing this specimen, and here I'm going to show you just basalt from Idaho National Laboratory. It's from the CFPP project, carbon-free power plant, better known as a nuclear reactor. So that's just playing with words that they do. But here we go, setup process. First, once we have the carved specimen, again, that's the bigger of the three, the biggest of the three. And specimen's got to be glued to this base pedestal to start out with. So it's not what you see everything here. It's just, it's epoxied. That's not that epoxy. It's epoxied at the bottom end of that. Then you'll put the top cap on, you'll epoxy that to it. Put the membrane on, epoxy the membrane so that we can keep it sealed down here. O-ring on the top to have it sealed. And you can see the time to set up a rock specimen is 4 days, because you're epoxying, you got to let it cure and all that sort of stuff. So then we will put it in the device. Oops. We'll get it here. And this just shows you two different types of basalt that we have been testing. And you have the vesicular basalt. You'll see data from 8 specimens. And, you know, those are the little pores in there. Those are the ones that make it more difficult to test. This is the bottom of the specimen at the top. Now, I say that because over here, here's the top of the specimen and there's the bottom, but I wanted to show you the bottom because we also have a little piece that goes into all the specimens. And what it is so if air is coming through the membrane, you know, just very, very slowly, you still don't want it to build up. And so we can drain, if we've ruptured a membrane, the air will be coming through fast and we can keep track of that. But we're taking great efforts to try to make sure we know what we're doing and getting good data. You can see length, let's say call 11 centimeters, diameter 3.8, and L over D at 2.89. Gives you a sense of our specimens. You're going to see vesicular, you're going to see vesicular and you're going to see alphanitic basalt specimens, 9 of those. That just shows you the total, the devices inside all of this chamber, and you can see we go up to 320 psi, better known as about 22 atmospheres to U. And you know, it's a lot of work to get all that set up. Whoops, I'll learn here. This is a little advertisement, and it's a little bit of a stretch because in this area, it's nice and clean, huh? Well, I'll get it. It's nice and clean. It's not usually nice and clean. There's a computer running a test, let's say, in there, and there's another one down here, you just don't see it. But what I really have enjoyed doing in the last 10 years maybe, you see this screen, and you can't see it very well. I can see it, I'm gonna show you. So here's a resonant curve that's on a sample, okay? There's how it's going. So you don't have to, you can go in and out, you can see if the test is going well and so forth. It's just a really nice thing to see the response that you should understand. And we have that now, which makes me very happy. And when we test these specimens, we'll test them. First off, we'll estimate, oops, oh, that's the one I want you to see. But we'll estimate the mean effective stress in situ, okay? And we'll then try to do 6 loading stages. Now, if you'll say that at 0 confinement is a loading stage, then that's one of our 6. But here we go. And then there's a fourth of what we think the mean effective stress is in situ, 2.5, the mean effective stress, 2 times and 4 times. Now sometimes 4 times, given the depth of the rock, we can't get to because we can't apply that much confining pressure. But that's typical. This would be the best we can do. And then we will unload 1, 2, and 3 stages. So we'll keep track of the rock and how stiffness and damping is changing or not with all that we are doing. Here's our core. That would be a typical core that would be sent to us. We haven't touched it. If we cut it here, we wanted to shorten it, and we cut it. You know, when you cut it, you have water in the blade when you're on the rock. That changes the rock's characteristics. Water in the rock changes it from a dynamics point of view. If you're doing static, it's okay. If you're doing what we're doing, you'd be surprised. And I think people don't know that at all. What you see also here is when we send it to Houston, we've done the tests on this. We send it to Houston and we would get this sample back. That's the one that I showed you. That's the big one. They would take and cut that sample out right here. Well, sorry, right here, Yeah, it's this solid one is going to be here, and then out of this is going to come that one. Okay, so that they do wonderful work down there, and we sort of discovered them by accident. Again, as I indicated to you, we're only going to do the largest of all the specimens. Okay, so here we go. Here's the effect of isotropic confining pressure, and you see there's no effect, on void ratio. So here is our unconfined estimated void ratios by measuring it. Then this is measuring the height change and so forth. And you can see the vesicular basalt is in black. The aphanitic basalt, almost no voids, and vesicular has some in red. And we're going up to, as high as we can go, 22 atmospheres or something in what we're testing. Not affecting this basalt at all. Okay, we're going to look at the effect of confining pressure on the basalt. And again, you see unconfined, because we would test that before we installed it in the device. And you can, because that's the only way we could really do that. But you can see unconfined, and then you see the confining pressure. Again, those are horizontal lines, that you're looking at. So no effect there. On Gmax, obviously there's also going to be no effect here, but we'd like to look at the velocity as well. Some effect of isotropic confining pressure on Dmin increasing with increasing sigma for some specimens. Okay, so what you see here at these lower pressures, there's not much effect, but now you see the red, so that's our almost no voids, and you see the black even in here. So on some of the specimens, I can't tell you why, but some do show a change. Now, as far as you're concerned, maybe that's no change. That's okay. But we're trying to keep track of all these little things to see what it might mean to us in the future in some of the work that we're doing. Okay, now here are so for all of those specimens, in fact, vesicular basalt has some voids. On those, here's the nonlinear curves. And this is the best we can do, going up. This would be no confining pressure and so forth. Starting out here, and there's a shear modulus, shearing strain, log scale. But you do see the nonlinearity that we can get to. We're not causing any damage to the specimens, because after we make each one of these measurements, not these really, but after you start to go nonlinear, you go back and you'd make that measurement, then go back to this level. Make that measurement, then go back to this level, and so forth. Just to make sure nothing's changing. What we're interested in is determining what might be a threshold strain for, we would call it the elastic threshold. When does it become nonlinear? Well, that looks like a nice linear relationship, doesn't it? I don't think you can get any better than that. And so right in here, we would be looking at that threshold strain. Here's for all of them, of the vesicular basalt. And you can see that you can't really attribute it it varies. There's no systematic reason that we can find, but the threshold strain ranges from about 5 times 10 to the minus 4% to 4 times 10 to the minus 3%. That's what you see there. Drew the lines in for you so you would believe me. In other words, I mean, make it easy to see. We would like to see when it started to change the material properties, but unfortunately our equipment won't let us go that far. Here are the one for the ones that have, and this is, I have to, I have to take and send this because the ephenitic basalt, and I saw that, has essentially no voids. There's a little mistake there, and in your stuff, that's my mistake for not catching that. In fact, I did catch it, but the person didn't get it changed. So I apologize. I just found that in the last couple days. But again, you see similar results, but they're high. It's a stiffer material. Okay. Again, not going through one at a time, but here we are. Our observations of the threshold, and again, 4 times 10 to the minus 4 to 2 times 10 to the minus 3, it's about the same. And you can see that the threshold in both cases is not well correlated with the modulus. Okay? So we just have to live with that. A first approximation is like 1 times 10 to the minus 3%, which would be almost like soil. Although you'd see just a huge change going to strains like this with soil. And soil, if this were soil, you'd see it'd be going like that and it'd be going there because it'd even be a log going to almost 1%, not 0.1% for shear strain. Okay. Not well correlated with Gmax, the first one. Again, 1 times 10 to the minus 3 for what you might expect. Okay, we're getting near the end. If you're going to compare it with some things, we could compare it with seed and Idris curve for sands, which may not make a whole lot of sense to anybody. That's okay, but just to look at a relative number. And so here we go, G over G max for the different basalts, and you can see they spread a bit, but they look good out here, but they aren't that different than, I mean, obviously they're stiffer, and the difference I think would be even further out here, that won't drop as fast than sand. So it's one of these curves that you can find easily in the literature, and we did. The damping, I suspect this damping for sand could be a little bit low, okay, but that's okay. But you can see how linear the basalt is, as you might suspect. Now, if you had a shale or something like that, there's going to be differences here from this material. So rock isn't all the same. This makes me feel a little bad. I may have to make an apology, but is Joseph's son around? How come? I thought he was going to be here because I have this just specially for Joseph. Joseph was pushing me hard. Yeah, take a picture of this, please. Joseph, you made me do this. Well, maybe not totally. This, I won't tell you where this curve came from, but it's in Tennessee. But we'll leave it at that. I might have to shoot you otherwise. But, you know, this is a shaly material and a different material. You'd expect this to be stiffer, but we maybe put that a little longer. Added a little more there. So you got to be careful. But what is the biggest difference? Look at that. I mean, there's like less than 1% and 3%. And that, some of this stuff was actually measured, but on very different materials. So rock is not rock. You have to be careful in what you're looking at. And the number would be different too. I didn't add this into this talk, but into the write-up, but when we have let rock resaturate itself. That is, we put it in a bucket of water for a week, okay? And then we test it. And we would do this free test that I'm talking about. And we would look at P waves, compression, so constrained compression waves. Is a rock gonna be, I just need to see, what? 5 minutes? No, I'm on a roll, huh? Is the rock unchanged? Is it stiffer? Is it softer? It's stiffer. Why? I told him, no. Good guess. Why? Because when the water gets in there and you're at the real high frequencies of that wave going through there, the water's got no place to go, and it's an overall stiffer system. That's going to happen in an earthquake too, just for the record, huh? What about damping? Oh yeah, damping goes up when water moves around in void space, particularly in sands and so forth too. I mean, that will really increase the damping in your system. So maybe, remember how Joseph was, thank you, pushing me to go beyond my means there, so I didn't do so well, but that's life. Just so you know, here, and this is in the paper, here are the 17 specimens, but it'll tell you the depth and so forth and the assumptions we've made, and that's also in the paper for you so that you'd have that. Okay, so in this study, a series of resonant column tests were performed to investigate the linear and mildly nonlinear, just because we didn't have any more power, to shear above about 2%. This allows you to go to very large strains and is better. Why? What's the effective radius on this? Well, we think it's 2/3. What's the effective radius on this? 2/3 of the diameter. The effective radius on this is very well defined, I mean, within a few percent. So hollow specimens are wonderful. And we have the data. This is the first time this data has been presented anywhere. So I had to be a little careful. Okay. Two types of basalts. Okay. The test results showed that linear and nonlinear dynamic properties of basalts are both pressure independent in these measurements to confining pressure of like 22 ASM. 320 psi for me. The range of linear and nonlinear dynamic properties are reasonably similar for the two types of basalts, and they weren't that different in terms of void ratio, but they were that different when you let them absorb water, okay? And in comparison with sand, of course, the basalt has a larger linear range than sand as expected. So that's a quick review of what we're now doing in a lot of our testing in the lab. And that's a lot more testing with rock because, again, when I've been out in the field, I see how people treat rock as if it's indestructible and you can't hurt it. Don't let it dry out and so forth and so on, because you can change some of the properties. Thank you.